This is a video tutorial that I'm preparing for the playlist that is intended to be used by people who want to transition from the ABAQUS CAE program to the 3D Experience interface or platform, or the people who are entirely new to the 3D Experience platform and would like to learn how to do finite elements on them. Uh, just to remind you, the native FEA solver for the 3D experience is actually the ABAQUS program. The particular problem that I'm doing is involving axisymmetric model, uh, which is involved with contact. And usually, the way I operate with these tutorials is that I find problems that have already been done with the ABAQUS CAE on YouTube, and they're in a step-by-step fashion showing you how to go from point A to point B. So what I try to do is to replicate the steps in the 3D experience in order to demonstrate how different they are when it's compared to the ABAQUS CAE. The icons are different, the interface is different, some functionalities are different, and therefore it's not a straightforward matter to go from ABAQUS to 3D experience. Now, the particular version of the 3D experience that I'm operating on is 2022x, and the reason is that it's a fast evolving software, and there are constant additions and uh, interface changes that they make, and therefore this particular one is geared to the 2022x. Okay. Now, the problem that I'm going to be doing is going to be explained in detail, and I would like to acknowledge the help of Mr. Martin from the LaSalle system, who helped me uh, get familiar with the ABAQUS, with the axisymmetric modeling in 3D experience. The problem that I'm doing is actually done by this well-known YouTuber, and I already made a video tutorial where this problem is done in a very particular way. The workpiece is modeled with 2D axisymmetric continuum elements, and the indenter is also modeled with 2D axisymmetric continuum elements. So what I want to do here is replace the indenter with an analytical rigid surface. Okay, so you see a workpiece here and an indenter that is pressing against it. I will model this indenter only as basically a curve which is going to be pushing against the workpiece. Okay. Now I will use the same element sizes that this gentleman is using, and nonlinear geometric effect is on. The material properties that the workpiece is made of is given here, and also the elastic plastic response of it, a very simplified elastic plastic response of it, is displayed here, and the dimensions are given below, and I will refer to these particular slides that are will be coming later on as we do the work. So let me get out of here, go to the 3D experience. Already I have created an assembly file here. Okay, so let me rename this thing properties, just so that in case we have to find it later on, at least we know how it's made of. So it's called Axi. I'll say surface slider. Not surface slider, analytical rigid surface. Analytical rigid surface. Surface. Okay, good. So we say okay. Let's go make the workpiece first. So insert, put the cursor there, right click, insert, a 3D part. right there. And I'm going to call, well, I can call it workpiece, but I'll leave it the way it is, so doesn't matter. Double click on 3D shape, and on the YZ plane, I will sketch this rectangle. See? Okay, so let's do that. Here's a rectangle. Let's give a dimension. This is 25 millimeter. And the vertical side is 10 millimeter. Okay. Now we're going to exit. And we're going to shaft this thing. Because when you do axisymmetric models in 3DEXPERIENCE, you actually have to create the object in 3D, and then the program itself makes a cut and gets a two-dimensional, basically, section out of it. Okay, so I'm going to have to go and shaft this thing about the z-axis. So you put the cursor there, right-click, and z-axis 360 degrees. So this is going to be the workpiece. Okay, what I need to do, what I would like to do is to create a geometric set, and this is very important that this point that I'm going to create is going to be in the geometric set. A point, and this point is going to be the origin of the axisymmetric coordinate system later on. Okay, so notice that on purpose I put it in geometric set, because this process I don't believe is going to work if you put it in the part. Okay, now also there's a point that I created. Also, I need a line here that eventually will be declared as the axis of symmetry of the 2D problem. Basically, you can make a line, or the alternative is I'm going to create an axis system here, and its z-axis is going to be used for that particular purpose. And let me uncheck this uncheck this current here. Okay, good. Now notice that the coordinate system has been created. It's right there. This is going to be used, its z-axis is going to be used for the purpose that we have in mind. We're going to apply our material properties. So let's go ahead to Tools, create a material property, and I'm going to call this thing Axi Rigid Analytical. I'll call it RS, Rigid Surface. Okay, and we're going to say OK. And this is going to be created, but it's a blank placeholder now. There's nothing in it. So just bear with me for a second. Let me see now. It must be somewhere here. Right here. Axis Analytical Rigid Surface. Put the cursor on it. Right click, apply. And I don't need this anymore. I'm going to put it on the part that I just made, and we're going to input the properties. So expand the tree, expand this, double click on it. Okay, so it's structural, ABAQUS multiphysics, mechanical, elasticity, elastic, and the Young's modulus of it was 100,000 MPa. Okay, and Poisson ratio was 0.34. And then, because we're going to look at the elastic plastic response of the workpiece, so expand the plasticity, metal plasticity, plastic, and check it. And the yield strength was 110 at zero plastic strain. That's what yield strength means, 110. And then at the plastic strain of 0.8, 300 megapascal. So 300 megapascal at the plastic strain of 0.8. And if you want, you can plot this, by the way. It's going to be that straight line that you saw earlier. So we say OK, and we're going to save everything. All right. Okay, now I'm going to the top level assembly, right click, insert, 3D part. And this is going to be the indenter. We're going to make it, double click on the 3D shape. By the way, here is my other piece, the work piece. Okay, on a convenient plane, on that YZ plane, I will sketch. Okay, how about an arc? That represents half of the indenter. Let's put dimension here. This radius is 5 inches. And I'm going to bring this thing down and put it on that face. So the distance with this point control that. Okay, so let's see dimension between this point and that line. We can make it 0 or say right click coincidence. It brings it down and places it there. Okay, exit. Now, I'm not going to put any material on this because it's going to be an analytical rigid surface. However, I still have to create the surface there. So to do the surface, I have to be in generative shape design, and I am. So I'm going to use the revolve, this sketch about the z-axis for 360 degrees. 360 degrees. Okay, there we are. And this is pretty much done. Except that I didn't put any material on it, as I said, and this is going to run into some minor issues that we have to clean up. Okay, once this is done, then we're going to go all the way to the top level, and we're going to go to the model assembly design and click on the automated FEM. Select the Axisymmetric option. Let me move this thing on the side. To be consistent with what we did earlier, and the other reference for the mesh size, I put 0.3. And now here, what's going to happen is that it's going to take this this surface, and put beam elements on it. But I don't need it. I'm going to delete those beam elements, okay? So, in fact, if you want, you can also say 0.3. It really doesn't matter. Mesh size here because you're going to delete it. And then, oh, here, don't forget, plane is YZ. You have to select these YZ. Origin is that point, and the axis is Z axis. So, or if you had a line there, you can also try this to see if it works or not, but Z axis definitely will work. Okay, and then say okay. What's going to happen is going to create the continuum elements right there. You can see that. In fact, if you say update, these messages are because it meshed this arc with beam element, but there were no properties on it. But that's not worrisome, because what we need to do is we have to go here and we have to delete this beam elements. Just delete it, and the properties that it said it didn't know what it was, delete it. So that's fine. In fact, if you update, you see that this is going to go away. Now, while we're here, we're going to create our analytical rigid surface. So we go analytical rigid surface, we select that curve, and for the point, we select this point as the reference point for this analytical rigid surface. We will have to come back and flip the direction later on, but maybe, I don't know, we'll wait until it crashes and then we're going to go and flip that. Okay, good. So that takes care of these. That's fine. Now we're going to go to the mechanical scenario creation. All right, so select for analysis type structural, and for the finite element model, select the one that we just created. And we say OK. We're going to go to our procedure. It's a static step. I'm going to use the same initial increment time as the reference 0.01. NLGeom is on already automatically. We don't have to worry about it. And we say OK. This is dummy time, of course, because it's static problem. Now, as for boundary condition, first of all, the bottom of this is entirely clamped. The bottom of this edge is entirely clamped. That's what I did. And the reference point, I'm going to make sure it only goes down. So we go and do a fixed displacement. This reference point only goes in the direction Z, direction R is fixed, and direction theta is fixed. And now we give it a translation. Here's a translation on that point in the direction Z, direction Z, you can see that, direction Z, distance of -1 millimeter. And we say, okay. Now, I have not defined any contact between these two, interaction between these two. We'll have to do that. But what we're going to do is we're going to run it and see that without the interaction, this is going to go through it, okay, through this workpiece. So let's go ahead and do a quick model check. And notice that these arrows, by the way, these arrows, see that? These arrows, you have seen them in the ABAQUS CAE, if you're a CAE user, when you did Axisymmetric model, but keep an eye on these. Later on, we're going to do something to it. Right now, there is no contact, so these arrows are irrelevant and just going to go through. Okay, so this is the scenario check. It's going to be quick. And then as soon as this is done, we're going to say simulate, and you see that it will basically go through the workpiece. Okay, good. This iterations tab is the equivalent of, or the counterpart of the monitor in the CAE job submit dialog box, job creation dialog box. You will see that the iterations, the increments is going to be very fast. That means there's no detection, contact detection, so it's going to just go through it. Yeah, extracting results, and it's kind of going to be useless because it's going to go through it. So let me close this. Right there, you can see, right there, it just went through it. Okay, good. So what we're going to do is create interaction. Go back to the scenario. First of all, define some kind of a contact between them. So we go here under interaction, define the type of contact, contact property, tangential behavior, specify coefficient of friction 0.5, which is the same thing that we did in the other video where both indenter and the workpiece were modeled with continuum elements. And for the normal behavior, I believe its default is hard contact, and we're going to keep that. Okay, so this is defining the contact between two, but now we have to see how the contact takes place, and I'm going to do that with surface-based contact. In the other video where I did continuum, I used the general contact, but here I'm using surface-based contact. For the main surface, we have to select the analytical rigid surface. To do that, I'm going to expand this, use the pull-down menu, go to the FEM feature and select the analytical rigid surface. Good. And for the other one, for the other one, I'm just going to use the top edge. You will see that even this, and there is no opportunity for flipping the direction of these guys. You can see that. You will see that when we run, this still goes through it. Okay, because these arrows are pointing this way. So the contact on the outside is not detected. It's detected on the inside, but there is no inside contact. So let's go ahead and run it. I'm not going to do a model check. We're going to run it and see that once again this goes through the workpiece, and that's where you have to go and flip the directions, and that needs to be done in a very special place. It's in this abstractions where we created the analytical rigid surface. That's where we have to change it. Again, it's going to go very quickly through these iterations and increments because there is really none. Just this thing moves as a rigid body going through the workpiece. See, just as fast. Definitely there's something wrong here. You can sense it. Okay, close that. And once again, notice that it did go through it. This is the initial one, and then gradually it goes through the workpiece. Okay, so what we're going to do is we will go to this abstraction branch here on the very top, abstraction, double click on the analytical rigid surface. This pops up and you just say flip the direction. When I say flip the direction, these arrows will go in, these triangles will go inside. You see? And the contact is, detected on the outside basically. So let's run it now. A scenario, go to scenario and run or simulate. This time it actually presses against that workpiece. And the numbers that you get are fairly reasonable and they're in agreement with what we did when we solved the same problem with continuum. So continuum rigid element for the indenter and the continuum deformable, of course, for the workpiece. I'm clicking on the iteration tab because I want to show you that actually the number of increments is a lot more, and this thing takes a lot smaller increments than what you saw earlier. The steps for doing the axisymmetric and contact and these rigid surfaces, these are not, although if you're an ABAQUS user, they all look familiar to you, but they're nothing intuitive that can be figured out just by, either looking at the documentation, unfortunately, or, yeah. There is some proprietary information from the SAW on their sites, and one can get hold of them by contacting the SAW systems, but not much in the public domain. Okay, it's reaching the end. Extracting results. Okay, close this, and you can see that actually it establishes contact, and yeah, these numbers are in line with what we did earlier. In case you want to see something else, this can be put in, by the way, a 3D display. So if you click on the display tab, click on this, this results option, you can make it the sweep 360-degree, uh, angle, and don't use 10, use something bigger because then you can see that it's very jagged. So use, I don't know, 50 perhaps. You can see a lot smoother. Now, let me close this. If you want to see this is the von Mises stress. If you just want to see, for example, the contact pressure, just hypothetically contact pressure, where's the contact pressure here? Right there. Well, it's underneath this, you can't see it, so what you do is you uh, uh, go to the tree at the very bottom under the display group. Okay, you can select, for example, you can select, see for a second, you can select this and it kind of puts it away and shows you the contact pressure underneath. Or if you do this, it'll come back the other way around. So the contact. Oh, this is sure. This is an analytical rigid surface, so it doesn't display it on the surface. Okay, you just yeah, the pressure is going to be appearing here. If you were doing continuum, then you would be able to see the contact pressure on this also. All right. Good luck.